Assalamualaikum. In this video, we're going to look at topic 7.3, Synchronous Counter Design for subject PEL 1223 Digital Electronic. In this topic, we're going to design synchronous counter using the knowledge that we have known in the previous topics. Right, before that, do you still remember the concept of synchronous counters? Let's say for up counters like this, we know that for synchronous counters, all the clock of the flip-flop are connected together. So all the flip-flop will work synchronously, right? And the JK inputs of each flip-flop is different. Look at, for example, here 3-bit synchronous counter, the flip-flop 0, flip-flop 1 and flip-flop 2, the inputs are JK inputs are different from each other, right? And in the next example, the synchronous decade counter or mode 10 counter, we can see that this counter, although it has 4 flip-flop, okay, but it only counts up to 10. Counts up to 9, and then it will recycle or go back to 0, 0, 0, 0. All right. To do this, we must supply the correct JK input for each of the flip-flop. Okay, so that the counter will circle or count up to 9 and then go back to 0. Alright, so for this class, for this topic, we are going to try to create or design our own counter. Okay, so far we've seen counters that count in normal binary or BCD count sequence 1, 0, 1, 2, 3, and so far we have seen counter counting up to 9. Okay, but how can we design our own counter that counts in a unique sequence? For example, instead of counting 0, 1, 2, 3, 4, and so on, we want it to count in the order of 1, 3, 5, 7, and so on. Okay, so to do this, we must decode the various states of the counter using combinational logic circuit. Then we must supply the proper logic levels to each J and K input to the correct time. Okay, before we can go on and design our counter, so let's look at the concept of counter decoding. What does it mean by counter decoding? Counter decoding is a process where we use decoders or logic gates to determine when the counter is in a certain binary state in its sequence. Okay, for example, shown here, let's say we want to decode when the counter is in condition or binary state 1, 1, 0. Okay, so what we do, this one is Q2, Q1, Q not bar. Okay, so for that purpose, we put a NAND gate here and connect it to the suitable output, okay, which is since we want to detect 110 or Q1, Q2, Q1, Q0 bar, so we supply the input of the NAND gate with Q2, okay, and Q1 and also Q0 bar. So therefore, when this condition or this state, when the counter is in this state, this NAND gate will produce high output. Okay, so that's how we decode counter.